Page 94. Organization and use of the periodic table. Recap, Section A. There are more than 110 known elements. Each element has a unique number of protons found in the nucleus of its atoms. The atomic number of an element is the number of protons it has. Elements with the atomic numbers from 1 to 92 are found naturally on Earth. The elements with the atomic numbers greater than 92 are artificially produced in a laboratory setting. These man-made elements are radioactive and very short-lived. Elements combine in predictable ways to produce compounds that make up other substances on Earth. Earth's crust is formed from compounds made of a relatively small number of elements, including silicon, aluminum, iron, sodium, calcium, potassium, magnesium, hydrogen, oxygen, nitrogen, and carbon. These same elements make up most of matter in organisms, bodies of water, and the atmosphere. An element may have an isotope. The atoms of isotopes of an element differ only by the number of neutrons in their nuclei. Section B. The periodic table is an organized display of information about the elements. Each element is represented by a box, like the one shown for lead below, which has a particular position on the table. The element's box usually contains the following information: the name of the element, lead, the chemical symbol, an abbreviation consisting of 1 or 2 letters. The first letter is always capitalized. Some symbols are taken from Latin names. Pb is from the Latin name for lead, plumbum. Atomic number. The number of protons in the nucleus, which is equal to the number of electrons in the electron cloud of a neutral atom. In this case, for lead, it's 82. The atomic mass. It's equal to the sum of the protons and neutrons in an atom's nucleus. On the periodic table, the average mass of the atom of all the isotopes of the element. In this case, for lead, it's 207.2. To find the number of neutrons in the most common isotope, round the atomic mass given in the box to the nearest whole number. So in this case, 207.2 would be rounded to 207. Then subtract the atomic number. So 207 minus 82 equals 125 neutrons. Section C. Color codes, symbols, or position give other information about an element on the periodic table. Color codes are often used to show whether an element occurs in a solid, liquid, or gas at room temperature. Most elements exist as solids. The only 2 that are liquids are going to be mercury and bromine. The boxes for all of the elements are arranged by increasing atomic number. The vertical columns in the table are called groups, or families. Elements in each group have similar properties because they have the same number of valence electrons. Valence electrons are the electrons in the outermost energy level of an atom. The valence number is the same for all members of a group. A period is a horizontal row of elements in the periodic table. When elements are arranged in order of increasing atomic number, a repetitive pattern of properties across periods is apparent. This is the basis of periodicity. Section D. Elements are classified as metal, metalloid, or nonmetal. Metals. In general, metals are lustrous or shiny in appearance, and malleable or ductile, meaning they can be molded into different shapes without breaking. Metals are extremely durable and have high melting and boiling points. They are good conductors of thermal energy and electricity. Metals are found to the left of a zigzag line or staircase, which is usually drawn between the boxes in the right half of the table. Most elements are metals. Metals have few electrons in their outer energy levels. They tend to lose electrons in a chemical reaction to form positive ions. Metalloids. The metalloids are 6 elements that display qualities of both metals and nonmetals. Metalloids border the zigzag line, or are part of the staircase. Metalloids have about half of a complete set of valence electrons. They tend to share electrons when forming compounds. Nonmetals. The nonmetals are a collection of gases, solids, and one liquid. Nonmetals are opposite to metals in most ways. They are dull in appearance. They are not particularly ductile or malleable. With the exception of carbon, they are poor conductors of thermal energy and electricity. Nonmetals are found to the right of the metalloids, or the staircase. Nonmetals have a complete, such as noble gases, or almost complete set of valence electrons. Those with an incomplete set tend to gain electrons during a chemical reaction to form negative ions. So here in this picture we see once again our organization. So all the darker grays are going to be our metals. All the light grays are going to be our nonmetals, including hydrogen. And all the white boxes are going to represent our metalloids. And the black line is a zigzag or staircase. Section E. An ion is an atom with a positive or negative charge. A positive ion has lost electrons, so it has more positive protons than negative electrons. Metals become positive ions in chemical reactions, such as sodium, which has a positive 1 charge. A negative ion has gained electrons and has a negative charge. Nonmetals become negative ions in chemical reactions, such as chlorine, which has a negative 1 charge. Summary of ways an atom can change. There are 3 different ways an atom can change. The first is if it loses or gains neutrons. In that case, it would become an isotope, meaning it would have a different mass. The other way is if you change or lose or gain a proton. If you change the number of protons, you have a completely different element, okay, because it has a different atomic number. The third way you can change an atom is if you gain or lose electrons. And in this case, you would become an ion, so it would have a positive or negative charge. Section F. Atoms gain, lose, or share electrons to become chemically stable. An atom is stable when it has its maximum number of possible electrons in its outermost energy level. In class, we call this F full, or happy atom. This is normally 2 or 8 valence electrons. The chemical properties, such as reactivity, of an element are determined by the number of electrons in the outermost energy level, or valence electrons. The more electrons that are needed to make the outer energy level complete, up to 4, the less reactive the element will be. The most reactive metals only have 1 valence electron. These are in the alkali metal family. An atom needs to lose only 1 electron to become stable. The most reactive nonmetals are the halogens. A halogen atom has 7 valence electrons and needs only to gain 1 to have a complete outer energy level. The noble gases, such as helium, neon, and argon, do not react. Their atoms have a complete, full outer energy level. Section G. Compounds are formed when 2 or more elements react with each other. An electrical force, or bond, holds atoms together in a molecule of a substance. When 2 nonmetals react, atoms share electrons and form a covalent bond. When a metal element reacts with a non-metal element, an ionic bond is formed. 1 or more electrons are transferred from one atom to another. Atoms of the metal lose electrons, and the nonmetal gains electrons. The ions formed have complete outer energy levels. Therefore, they are both stable. Section H. A chemical formula represents the number and kind of atoms in a molecule. Chemical symbols identify the elements in a molecule's chemical formula. A number to the right of and slightly below a symbol is called a subscript. It represents the number of atoms of an element in a molecule. If there is only 1, 1 is not written. O2 means there are 2 atoms of oxygen in one molecule. H2O means there are 2 atoms of hydrogen and 1 of oxygen in one molecule of water. Parentheses in a chemical formula enclose atoms that act as a group. So in this case, OH is acting as a group. CaOH2 is the chemical formula for calcium hydroxide. There are 2 hydroxide, OH, groups in the molecule of calcium hydroxide. So the molecule has 1 atom of calcium and 2 atoms of oxygen and 2 atoms of hydrogen. It's kind of like in math class where you distribute. So this 2 means that there's 2 oxygens and 2 hydrogens. We're distributing the 2. This ends the organization and use of the periodic table section.